My name is Denise Lucy. I am a professor of business and organizational studies here at Dominican and the director of the Institute for Leadership Studies, which has the great privilege of partnering with Book Passage each fall and spring to bring to our community, to our campus, remarkable leaders from across the disciplines. And so it is just my honor to have been invited to also participate with the Big History program. And this is our third program over the last year, and it's just really been a terrific set of offerings, and it's a tradition that we've begun. And so thank you so much for inviting the Institute for Leadership Studies to be your partner. I also wanted to just put in a plug again for Book Passage that without their support, our programs could not happen. And I'm hoping that being an independent bookstore, you will buy local. Can I hear you? Promise me that? All right. Before I tell you a little bit about the programs we have for the fall, I wanted to mention that these events don't happen without great supporters like our students, our faculty, and staff volunteers. They're all here today as volunteers, and I hope they greeted you with the kind of spirit that we certainly have for one another, which is welcome. And may we thank them for their volunteering support, the Leadership Lecture hosts. Thank you. So before we have our program this evening, I just wanted to mention that I'd like to ask you to note when you walked in the auditorium, you should have been offered a program for this fall series. Have you received one? Great. And you can grab them, and there are some in the hall when you leave. So I hope that you'll put down some dates because these events will be sold out. September 25th, Salman Rushdie will be here in the auditorium, and he is going to tell that story that we heard about 10 years ago. And do we have some of the dates rolling, Rachel? We'll get some of the dates up there, so I won't have to give you all the specifics. But September 25th, that is a ticketed event, and you buy your tickets from Book Passage online, and you'll get a copy of the book as part of that ticket. November 14th, Ina Garten. Who knows Ina Garten? All right. Oh, well, I love Ina Garten. And Ina Garten is coming, and she's going to be in conversation with Melissa Mayer, the CEO of Yahoo, on November 14th. We hope you will join us. That's also a ticketed event. On the 30th of November, John Meacham, renowned historian, has written a book, Thomas Jefferson, that is a free and open to the public event, and we hope that you will be joining us. In the spring, we do have a few already organized. One is with Dr. Cecil Williams. The other is One Book, One Marin, which is held on April 18th. One Book, One Marin is an award bestowed on an author where the entire counties of Marin read in the spring. We won't announce that person until January, but we have made that selection, and it's the 18th of April. That person who wins that award will be here in the audience. Isabel Allende is coming. She's one of our wonderful neighbors and friends, and she always is a crowd pleaser. She's on April 23rd, and we have other programs that have not yet been confirmed. Please know that if you cannot make an event, or you would like to listen to it again, we have some of them on video. Tonight's lecture is being videotaped. It will be on our Dominican website and also rebroadcast on the Community Media Center for Marin on Channel 30 on Wednesday nights at 8 o'clock. And lastly, Penguin Radio is broadcasting live, and we'll have a podcast. And we'd like to thank our wonderful Professor Stuart Horn, who is the great radio man behind the scenes. So thank you, Stuart, for your support. Now, last but not least, in order for us to host these programs, we need to find supporters. And last year, for the entire academic year, of which we had 13 great events, we had a remarkable sponsor. Private Ocean Wealth Management supported our programs all year last year. Private Ocean is one of the oldest and largest privately held wealth management firms in Marin. It's been in the top 100 registered investment advisors nationwide 7 times by Worth Magazine, and in San Francisco Business Times names it 4 out of the top 25 independent registered investment advisors in the Bay Area for firm quality as well as assets under management. This is a terrific organization, has recommitted to us, and they will be supporting these lectures for the rest of this academic year. So would you please, on behalf of the institution, thank them? It makes all the difference. And we have the good fortune to have their CEO, Richard Stone, among our Board of Trustee members. Isn't that a wonderful opportunity? It's a great thing that he's part of our community. And he is here tonight, and I'd like to introduce him. Richard Stone has served as a leader in the wealth management business for over 40 years. He is the co-founder of Private Ocean. He was recently awarded the prestigious Charles Schwab Impact Leadership Award for his lifetime contributions to the financial planning industry. And Richard is here tonight, and he's going to introduce Dr. Mugen Bhima, and I'd like to have you welcome Mr. Richard Stone.
As a trustee of Dominican University, it gives me great pleasure to welcome you to the Leadership Lecture Series featuring this engaging big history conversation. The Leadership Lecture Series highlights acts of leadership across disciplines, featuring leaders in the world of business, politics, literature, psychology, civil rights, and entertainment. Private Ocean is honored to provide support to this important community-building opportunity for the Dominican campus, welcoming Marin and Bay Area community members to engage around powerful ideas and actions. And welcome to our freshman students tonight who are enrolled in Dominican's Big Histories General Education Program, and to their faculty who are leading them through this fascinating big history story. Private Ocean is honored to help support this fine educational and community program. This evening, I'm delighted to introduce Dr. Mugen Bhima, Director of Dominican's General Education and First-Year Experience Programs and Associate Professor of English. Dr. Bhima has developed the Big History curriculum with a team of professors from many disciplines across the Dominican's campus. She will provide us an overview of Big History goals and introduce our special guests for this evening's lecture. Please welcome Dr. Mugen Bhima.
Thank you. All right. Good evening and a warm welcome to all, but a special welcome to our first-year students who are just now in their second week of classes. Hold up. Glad you're here. So I'm Mugen Bhima, Associate Professor of English and Director of First-Year Experience Big History. Tonight's event is part of our year-long curriculum in Big History, a unique program that takes the participants on an immense journey through time, 13.7 billion years of it. We witnessed the Big Bang and the first moments of our universe, to the birth and death of stars and planets, and the formation of life on Earth. We observed the emergence of the web of life and the dawn of human consciousness, and follow the ever-unfolding story of humans as one of Earth's dominant species. In studying the past, the natural and human history of our universe, we seek to understand ourselves. In engaging with fundamental questions, we examine our own individual and collective agency regarding our role in shaping the future of our planet. Following in the tradition of the Dominican sisters, we learn and share a new story which we hope will come to define us as a community and a people. Dr. Fred Spier's talk tonight, which focuses on big history and the future of humanity, is a wonderful fit for our program. Before I introduce our illustrious speaker, I would like to thank you all for being here, our Dominican community, and all the big history enthusiasts. I know you're out there because I've seen many of you and said hello to you tonight. I would also like to extend a special welcome to our resident big historian and Dominican Professor Emerita, Dr. Cynthia Brown. Cynthia, could I ask you to, the author, and for the freshmen, she's the author of your textbook. I would also like to welcome a past big history speaker here at Dominican, Dr. Brian Swim, who has kindly returned this evening to be in our audience. Yeah. Many of you might remember him from last year's keynote address and the lecture series, Journey of the Universe, a film that also won an Emmy. So now, last but certainly not least, on to Fred Spier. This evening's speaker, Dr. Fred Spier, comes to us via the University of Amsterdam, where he is senior lecturer in Big History. He has organized and taught the annual Big History course at the University of Amsterdam since 1994. The annual Big History University lecture series at the Eindhoven University of Technology since 2003, and the Big Questions in History course at Amsterdam University College since 2009. This man knows his big history. Dr. Spier, in true big historian fashion, has a multidisciplinary background. He has a master's in biochemistry, a master's in cultural anthropology, and a PhD in cultural anthropology and social history. As part of these studies, Dr. Spier executed a 10-year research project on religion, politics, and ecology in Andean Peru, which led to the publication of 2 of his books, Religious Regimes in Peru and San Nicolas de Zorite. His focus has been developing a paradigm that helps to explain all of history, which he has elaborated on in his most recent book, Big History and the Future of Humanity, which was published in 2010. This book has already been translated into Spanish, and translations into Chinese, Arabic, and Korean are underway. In addition to promoting big history in many different arenas, Dr. Spier was a co-founding member, like Cynthia Brown, of the International Big History Association, and he currently serves as the association's vice president. And here's a bit of good news for us. We are pleased to announce that Dr. Spier will also have to return to Dominican in 2014 because Dominican University of California has been selected to host the 2nd International Big History Association Conference in August 2014. We're very pleased. Go Penguins! So, please welcome Dr. Fred Spier.
Thank you very much. I hope you can, yes, I think the sound is working well. Thank you very much. First of all, Dominican University for inviting me to speak here tonight. I feel extremely honored to be here at this university, which is the first university in the world that has gone big history. And as a result, you are setting an example for the entire world, and the world is starting to notice that. So I'm really, really very honored to be here. So thank you very much for inviting me. I know many people have been involved, but especially Mosgaan, who just spoke. And also I'm very honored to have so many people in the audience that have come and have an interest in big history. So let me say a few words about my thoughts on big history. I'm not really sure whether all of you are familiar with big history. I'm assuming that most of you are, but perhaps not all of you. So I would like to say a few words about the concept of big history first. It means the entire history of everything, from the beginning of the universe until life here and now today, where we are. And that's a very different type of history than traditional history. And as a result, you have to take a little bit more distance from your usual daily occupations or whatever you're doing. You have to think of yourself as being somewhere on the surface of this planet, this blue marble, out there in the black universe. You're sitting on this surface. Actually, we're very, very close to the universe, if you look at it this way, and we share a common past all on this globe. And so if you look at it from a bit of a distance, that's the picture that you get. And this is the picture that I use. I'll say a few more words about it later to help clarify this approach to my students. Now, if we look at the current story of big history, you can conceptualize it as a timeline that starts with the beginning of the universe here, everything packed together in a way that nobody can describe it, and it started exploding very rapidly, and in that process energy and matter separated. The first tiny particles formed, then a little more complex particles formed, and at a certain point things became so dispersed that gravity could kick in and you would get the first galaxies and stars. So you get star formation, galaxy formation, and as a result you also can get planets, especially when in large stars heavy chemical elements have been forged. That could not happen at the beginning. It went too quickly. Only light chemical elements would form there, like hydrogen, helium, not a lot more. But over the course of time, over billions of years, you get big stars that create large elements, large chemical elements inside of them, and when they explode, they blow it out across the galaxies that they're in, and as a result, they create the circumstances for more complex forms to emerge, like planets. And after a while, it can happen that on one planet at least, but there may be many planets out in the universe where that has happened, life started to form. And then we get the story of how life formed, developed in relation with the changing surface of the Earth, changing geology of the Earth. And at a certain point, humans emerged about 4 million years ago on the African savannas. And then at a certain point in time, we get our current history, but that's very recent. Now, this picture was designed by this couple. This is my colleague Eric Chasen, astrophysicist who teaches cosmic evolution at Harvard University. This is his wife Lola, who designed this timeline, this arrow of time. And this was her first design. They still have it on the wall there in their house in Concord in Massachusetts. So this is basically big history in a nutshell. So this means that now you've all become big historians, right? Now you can also wonder, where is big history on this timeline and where is human history? And I'll be very immodest and use my own book for this calculation. And if you want to find human history on this timeline, you have to go to the last page of the book, the last page of the index, on page 272. That's where you'll find it. And I came to this conclusion by calculating the number of letters in the book and basically dividing that by the number of years. So 13.7 billion years divided by the amount of letters in the book. So what you get is then one letter equals about 18,000 years. So basically, this is where you find the emergence of early humans on the African savanna, about 4 million years ago. This is where you find, oh, that goes way too quickly. Hold on. Not really sure what's happening, because, okay, let's go back. Here you find, let's say, the first human that was sort of developing a bigger brain, would make tools, could perhaps speak a little, Homo erectus, 2 million years ago. For some, okay, I have to point probably more towards the computer to make it work. And then about 200,000 years ago, Homo sapiens emerged, again in Africa, started moving out over the world. And then here we find 30,000 years ago that Neanderthals disappear. This is the coldest part of the Ice Age. So you can see there is not even one single letter left for traditional history. That's very little, right? So that sort of shows how insignificant we are in terms of cosmic history. At the same time, you also have to realize we are very, very special. We are a very unusual form of complexity, one could say, and therefore we are very special. So it is both. In terms of the timeline, it's hardly anything. In terms of unusual complexity, we are really remarkable. Anyway, so why would we do this? I always start my course by posing this question and giving some answers and say, okay, at the end of the course, we'll return to these answers and we'll talk about what you think. But I think what is really important, what really matters, is that big history answers all the big questions concerning how everything has emerged. It is a set of origin stories, origin of matter, of energy, of galaxies, of stars, of planets, of our Earth, of life, how everything around you, including yourself, has evolved. There's no other way, other form of history that does that. It's absolutely unique. So it is a modern origin story. Hold on, I have to point again to... I have a bit of a problem with the pointer. I'm not really sure what's going on. Let me check to see. There it goes. So I'm probably too far away. What it also does, and that's very important, it offers a framework to which you can connect all your knowledge. So if you want to know about Big Bang cosmology, you have to be here, of course, in the timeline. If you want to know about human history, you have to be somewhere here. If you want to know about life and geology, you can go all the way here. And you can, of course, refine this timeline, and basically you can connect all your knowledge to this frame. That's extremely important, because suddenly you have some kind of a order and no longer a big chaos. When you walk into a bookstore, you can say, okay, this subject belongs there on the timeline. This is about that. So it helps you to understand everything in a more organized way. And as a result, what it does, it provides you the best possible overview where we are right now in time and in space. There is no other form of history that does that. And this means that it may also help to prepare ourselves better for the future. This is something we cannot know in any way because the future isn't here yet. But given the fact that we have an overview, we're trying to create overviews of all these large processes that have happened, it may provide the best possible starting point for discussing the future and trying to create scenarios of what we would like to happen. Okay, well, here you see two of the major driving forces here in Dominican University. Mosgan, you've seen her, and Cynthia, she was just mentioned. This picture was taken in Beijing last year when they were presenting their case at the World History Association conference. This slide I use to promote Dominican University wherever I go, to make clear that, yes, this is a great example. You've got to do it too, right? And look at what these guys are doing. So that's why I'm showing it to you. There we go again. And I want to introduce you to a major big history pioneer. That is David Christian. He has been teaching big history since 1989 at Macquarie University in Sydney in Australia. What he did was design a course where all the specialists from the different fields told their part of the story. So astronomers would talk about astronomy, geologists about the history of the planet, biologists about biology, etc., etc. So you get a very coherent story, and he connected human history to it, and he coined the term big history, actually. This picture was taken at our big history conference in Grand Rapids a few weeks ago, where he was very happy to see big history take off in such a wonderful way. He wrote a book summarizing his course and his insights that was published in 2004 across the bay here at the University of California Press, which has set a standard for big history. And this man provided a course model that other people have started to follow, including us in Amsterdam. What happened was that my former supervisor, Joop Gouwsblom, I'll show you, here he is, he happened to visit David Christian in Sydney in Australia in 1993. He brought back his syllabus and asked me to start organizing such a course in Holland with all the possibilities and constraints that we had. So we started in 1994, and here you see our astronomer explaining the Big Bang, right? And our students, and we had lots and lots of students who were very enthusiastic. They were very eager to learn and discuss, and suddenly felt they had a new kind of overview of everything that they felt was very helpful. And we've been teaching this course ever since. As you can see, time has not stood still. It's been quite an effort, I have to say. I'm not going to tell you all these stories, but yes, it wasn't easy to establish big history at our university. But we've done it, and we've got some wonderful support, and as a result, we have survived and been able to actually expand. Now, just a few words of where I come from and why it would be that a person from such a small place would be speaking here tonight. What is it about Holland that probably might not even know where it is? So it's here, right? Here it is, and here are you. And this is Amsterdam, a familiar picture with canals and a Westertour, lots of bikes there. We basically bike around the city. Also, professors go to lectures on their bikes. Here you see the building where I'm currently located, the science building. You see just a small portion of the bike park. That's just regular life in Amsterdam. And just to get an idea where Holland is, so it's here in Europe, right? And Europe is divided in many countries, trying to become united as in the form of the European Union, but still pretty much divided. And it's a very small place. Just for comparison, if you were to fly from the east coast of the US to the west coast, which I did to come here, this is the distance from Amsterdam to Baghdad. So just to get an idea of how small and diverse Europe is and how small Holland is. So why would it be that big history would take off there? Well, I think that's because Holland has quite an interesting globalized history. Here you see Amsterdam harbor around 1650, as you can see. Then people were going all around the world for profit, trying to find whatever they could find that would make a profit, basically. What that was required is that for doing that, going on these sailing ships around the world, you would need good maps. You would want to know where are we, how can we set our course, what is it needs to be done. So Holland became a major force in map making, very famous force. And here you see some of these pioneers showing off very, very solid Flemish and Dutch persons showing their knowledge of the world, trying to sell their business. And that map-making tradition still exists. You may not be aware of it, but right now in Amsterdam is the home office of TomTom GPS. It's one of the big players still in the map-making world. And that is remarkable for a small country, right? That we are doing that. It's just a few miles from where I live. But it also requires sky maps. You may wonder why, but if you want to orient yourself on a sailing boat, you need to fix your position with relation to the sun and the stars. And that meant that people started making very precise observation of these things, create tables, so they could figure out where they were on the big seas. So you got these handbooks, like this book means Mirror of Navigation, of Sea Navigation. And these were also translated in different languages, became very popular, very important knowledge. So people started basically to orient themselves both in time, or in maps, and in the sky. And that is still the case. But just an example of what happened around, let's say, 1650. This is the town hall as it was built in the middle of Amsterdam. Right now it's the Royal Palace, but it was built as a town hall. And when you go inside, what you see here is world maps and sky maps. So basically these burghers literally walked on top of the world and the sky. And that's how they felt. I mean, we are the big players. We are the big global players. And they're expressing themselves in that way. The word globalization did not yet exist, but the image certainly did. And that astronomical tradition still exists. Holland is still pretty good in astronomy. Just to give a few examples, if you look at the solar system, this is the sun, these are the inner planets like Venus, the Earth, and Mars, and then you have the outer planets, and here's the yeah, it's not really a planet anymore, Pluto. So basically we're here somewhere, very close to the sun. But beyond that there are two major areas. One is called the Kuiper Belt and the other is the Oort cloud. And they're both connected to Dutch astronomers. Jan Hendrik Oort was a Dutch astronomer who basically discovered this big cloud. Another one, Gerard Peter Kuiper, who lived most of his life in this country, became aware of this cloud. And this cloud is becoming more and more important because it discovered more and more objects like Pluto beyond. They're called Kuiper Belt objects. So for a small country, that's quite a presence, right, in the solar system. A country of 16, 17 million people. Like a small US state, I would say. So it's not entirely surprising, given such a tradition, that there is an interest in big history in my country. And that is probably why I was able to get it off the ground. But now, a very different story. When I was a little younger than most students here, I was, 16. There was this Apollo project taken off, right? People wanted to go to the moon and they wanted to beat the Soviets. That was the idea. And here you see the first group of astronauts, Frank Borman, James Lovell, and William Anders, who would actually leave Earth orbit, go to the moon, circle it 10 times, go back as some kind of an exercise, preparing the way for a lunar landing. And this is from the press kit at the time before the flight took place, and this is what they expected to see. So the astronauts basically watching the moon and communicating with the Earth in distance. And then something sort of unexpected happened, but I'll say a few more. This is basically, I was at the time was fascinated by it. So live TV transmissions were suddenly possible. That was thanks to the fact that communication satellites had appeared. It was still black and white, and there were no video recorders yet, so I was snapping pictures off the screen because I didn't really know whether anybody would preserve that. So here are the pictures that I snapped at the time. What you see here is the launch, the separation of the first stage, astronauts on their way to the moon. This is the Earth from a distance, and this is, let's say, the moon. But it's all pretty fuzzy, right? It's not very impressive. But what was very impressive was this picture that they brought back, the view of the Earth at a distance from lunar orbit. It's become known as the Earthrise photo. This is from Time magazine. When I saw that, I was stunned. I tore it out. I stuck it onto the wall with pins. You can see here the hole still, right? I still have it. And yeah, that changed my life. It made me feel, and I think many others felt that too, that we had suddenly a very, very different perspective on our own planet. Nobody had ever really watched it from a distance, and suddenly there it was, as a blue marble in space, and it made me wonder, like many others, what are we doing to our planet? Are we basically creating a big ecological mess? And what I wanted to know was, how had we got ourselves into this mess? How did it happen? Could we understand history and as a result create perhaps some kind of a discussion platform for dealing better with the future? So I wanted to know how we got ourselves into this situation. And I think you can describe my career reasonably well by saying that yes, it started with this picture in 1969, and then about 40 years later I have the feeling, yes, I figured it out, at least in a way that I feel satisfied myself. And I'm not really sure whether you are satisfied, that remains to be seen. But yes, I think, yes, this is how it works, and it helps me to understand how we got here, and perhaps also what needs to be done. And that's what I want to talk about now. But first, a little more about the difference between big history and, let's say, traditional history. Traditional history is about big events, about wars, about kings, queens, all these discoveries, all these things. Is very different from, let's say, the scheme of cosmic evolution. But interestingly, if you just go back a few centuries, in fact, no more than 1.5 centuries, that difference did not yet exist in our societies, both on this side of the Atlantic and in Europe. And that may surprise you, but that's the case. For example, here's an example. It's a Dutch example. It's a history of the world written by a Dutchman, but probably copied from German and English sources, because there are plenty English, German, French, and probably also other languages of these similar histories. And what these histories consist of is they start with the biblical account of creation, and then, of course, through the big flood, and then down to what happened in Mesopotamia, and then basically they start to sort of put in all the history that they knew, that they had acquired up to their present day. So in a sense, it was a big history. It was not an academic big history, because the first part was based on a religious tradition, but it did answer all the big questions. All the big origin questions are here and are being discussed. And this is a tradition that actually goes back a long time, deep into the Middle Ages, perhaps as far back as the late Roman Empire. You can find examples of this type of history. So, in a sense, big history is not really new, it is actually rather old. If you are willing to consider this some kind of a incipient big history. Now, as an aside, how did I become aware of this book? Well, the reason is very simple. My granddad, here you see him, used to collect big histories. And I inherited some of them. So that's how I found out about this type of history, and then I started to explore that, and I found many others. And then I started to collect big histories in the United States, actually, during my visits here. And here you see an example of such a book that was published in 1837. It was Peter Parley's Universal History. That was a series of books written, say, under the name of Peter Parley, who was a fictional personality, and there were all kinds of ghost writers who would write their part. So this was about history, but were all Peter Parley stories. And this particular history was written by Nathaniel Hawthorne. And it's basically the same structure. Starts with the biblical account, goes all the way to the present day. And then what you see is around 1850, things start to change. Here you see an example of when things start to change. This is a book, a similar kind of work, written by this school teacher, Joseph Worcester, from Massachusetts. And it was also some kind of an all-encompassing history. This was required reading for freshmen at Harvard at the time. So in that sense, Harvard was then doing big history. No longer, but then it was. But what you see in this book, and that is very interesting, that doubts are creeping in. And the reason is that the modern science of geology, which has brought to light a vast number of important and interesting facts previously unknown, has produced a conviction among men of science that the origin of the Earth is to be ascribed to a period far more remote than has been heretofore supposed. And the most learned Christian divines have adopted a mode of interpreting the Mosaic account of the creation, which is in accordance with this opinion. He didn't explain how he did that. But what you see is that they're taking distance from it. They're saying, oh no, it is different. We have to admit that the Earth has existed for a much longer time. So there you see something very interesting happening, that people taking distance from the traditional account without being able to actually provide a new account. What is happening actually is that around that time, the modern historical profession is emerging, and that goes hand in hand with the emergence of nation states. Nation states like the United States or France or Britain or Germany, or in Central and South America, all these countries, they all want to write their own history, hopefully a good, proud history, so that people can feel good about their own country, that you create good citizens, right? That is the idea. And therefore, these historians get established at all universities, and usually the let's say, the professor who teaches their own history is the most important person in that department. So what you're teaching and what you're trying to create is a story of the origins of your own state, and you place it into a wider context of how it got there, and that's usually the Western Civ trajectory, which was formulated around that time. So that is the kind of history that you get, and there's a great emphasis on literary sources, and get rid of the biblical account. That doesn't count anymore. So what you get is a history that goes back to about 5,000 years ago, and all the rest doesn't matter anymore. And that has become the established history. And that is something very different from big history, of course. But the result was that, in fact, almost all the big origins questions disappeared. They were gone, and nobody was paying attention to them anymore, because there was no credible academic account for it. Yet, at the same time, people were thinking about how can we do that, but even a radical like Darwin, right, was very skeptical. He said it's merely rubbish to think at present of the origin of life. One might as well think of the origin of matter. Well, that's what we're doing right now in big history. But at that time, that was considered complete nonsense by him. Yet, at the same time, scientific discoveries continued, and that changed our view, and that made it possible to create a modern big history. Say a few words about that. Let's go back about a bit more than 100 years. The image of the universe was that basically it's the Milky Way, and we are in the center of the Milky Way. That had been discovered by this man, William Herschel, German origin, but mostly living in England, became an English astronomer. And he had done that by very carefully counting stars. That's how he would do that. He used that kind of telescope, and they would observe at night. He would observe, and his sister would write down the observations by candlelight. Right? That's how it worked. Well, you can imagine that you can observe star positions like that. It may be difficult to do a lot more than that. Now, this is the current view. We are here in the Milky Way. We're not in the center. We're somewhere in the suburbs, one could say. Not really far out, but certainly not close to the center. There's a very clear reason for that. And there are hundreds of billions of galaxies, and they're all part of an expanding universe with a clear beginning, the Big Bang. Now, I'm not going to tell you how scientists discovered that, but the major developments that were necessary for that to happen were basically people were able to capture more light. Bigger telescopes and the invention of photography. So you could basically get photographic plates instead of drawings by candlelight, right? So this is the difference. This is Edwin Hubble in the 1920s with this big telescope, but more importantly with a photographic plate that could show what happened and was far more precise than any other measurements had been before. And that made possible to do all kind of physical analysis. So astronomers turned into astrophysicists. And that made it possible to construct an entirely new story about the universe that is now in the form of starting 13.7 billion years ago all the way up to the present day, with in the beginning all these light elements forming, then later heavy elements forming in the stars, exploding through the galaxies, and as a result get planets that can support life like our planet. Well, that's the kind of story we got, and that's a story that was developed by scientists, not by historians. And historians hardly took notice, I think. They had no idea that this was happening, but some scientists realized, hey, this is a big change. This is something very different. As a result, we have to re-evaluate the place of humanity in the cosmos. And some of these scientists started writing about it. And because of this synthesis, it became suddenly possible to create this big story, the story of cosmic evolution, and then you could connect human history to it. And that is what David Christian and some others did. And that made possible big history in its modern form. So, for quite some time, there were some, let's say, people here and there teaching big history, but we didn't really feel that there was a lot of coherence. Sometimes we felt, well, you know what, we're pretty lonely out here, nobody seems to be paying a lot of interest. But that changed a few years ago, and I'll tell you what happened. And as a result, we decided during a meeting that was organized by Walter Alvarez, you can see him here, who's teaching at Berkeley across the bay, he's teaching big history there, the famous geologist who, with his father, came up with the hypothesis that there was this meteorite crashing down 63 million years ago that would have ended the dinosaurs and made room for mammals to thrive, and as a result, that's why we're here. And here you see the place where he discovered that, actually. So here below, that's the period that there were dinosaurs. Above here, no dinosaurs. And he discovered a thin layer of a certain chemical element, iridium. It was enriched there, and it would have come from this meteorite. That's the idea. So he took us there on a geological field trip for a week, and we decided during a meeting 2 years ago to start our Big History Association. And you see David Christian, this is Cynthia, of course, Barry Rodriguez from University of Southern Maine, Craig Benjamin from Grand Valley State University, that's me, it's my son, and it's Lowell Gustafson from Villanova University. So this gang decided, okay, we're gonna try and see what happens. And major reason was that we suddenly got a very important, fan, one could say, and that's Bill Gates. You probably are aware of the fact that Bill Gates is a great supporter of big history, but what happened was that he happened to listen to David's audio tapes, or CDs rather, during his workouts on his home trainer, and he thought it was the most wonderful course ever, so he contacted David and he said, you know what, I wished I had known this course, I'd followed this course, I'd taken this course when I was a kid, and I want to make it possible for kids all around the world to take this course. So what's happening now is they're creating a website that will allow the teaching of big history for 9th graders worldwide. It's currently in a piloting phase, but next year, about this time, they probably open it for the entire world, so anybody can do it. And here you see David, part of a session on what he calls the knowledge revolution, and David gave a wonderful TED talk on big history. You can see it on YouTube, on TED.com. I can really recommend that talk. It's a great presentation. So, of course, that changed the game, and that's when we thought, yes, we can take the plunge and we can start our organization. And this is a picture taken during our first meeting in Grand Rapids in Allendale, where David is explaining what is going on with the Big History Project, as it's become known, the website for secondary schools. So that has become a major force, and we were very happy to find that we have now more than 250, I think 262 members of our Big History Association, more than we ever expected to have within basically a bit more than a year of incorporation. So that's all going well. We had a wonderful conference, a lot of positive energy, I would say. So things are looking well for big history. Okay, now let's look at how you can construct your story. How do historians reconstruct the past? I think they do it in two different ways. One is the way of a narrative, a story that people tell. And in a sense, I would say, all of you are historians. Because any story is usually about the past, can be about the future. Okay, this is what I want to do, but you can say, hey, you wouldn't believe what just happened, right? That kind of story. That is about the past. That is some kind of a history, which makes one wonder, when does a history or a story about the past become an official history? A very interesting question to which I don't really have an answer other than when it's written by a historian who has gotten his degree somewhere, right? But that is not a very satisfying answer. But still, is somehow how it seems to work. But I would say that for most people, narratives are the most engaging form of history. I fully understand that, I fully appreciate that, and I think that is simply how it's been working for most of history and how it's going to work for most of history. I don't think that we can expect most people to be deeply analytical. That's simply not how it works. But there are some people like me who just want to know, how does the whole thing work? You know, it is just not a story. I want to know a little more. I want to find out, how does it work? And then you go for some kind of a theory, some kind of an organizing principle that helps you to understand, that ties it all together. Now, that is not so easy to find. And I think the history of theorizing is full of difficulties. It is a very difficult thing to do. And it may never be completely satisfying. This is typically such an example. You think in terms of business cycles, for example. But there are some clear advantages for using a theory. First of all, you get a clear framework. It's clear why you make your choices of what you think is important and what you think is not important. With a narrative, there's no way of knowing why things are in the story and all the things were excluded. How would you know? You don't have any handle on it. With a theory, you do have a handle. Also, what it makes clear is that there may be large parts of the story that are missing, that are not there. You might want to know more about it. You might want to try to do some more research. It may or may not be possible to find it, but at least it makes clear to you what you have and what you don't have. So in that sense, I think theories are very, very important, very helpful. And also theories, if they're good enough, they help you to simplify the picture, which is the aim of science, to make it more understandable, to get a grip on it. You want to simplify it. You don't want it to be complex, you want it to be simple. So that's the kind of thing I've been trying to do, and that's the story I'm now going to tell you. So you can look at big history as a story about complexity, about things that are not simple, but more complex. And for example, you can think of the lunar surface here. We are here in lunar orbit. You can look at the Earth, and it seems to me that, yes, the Earth is a little more complex than the Moon, right? And when you look at the universe, there's hardly any complexity at all. So basically, if you look at the universe as a whole, complexity is pretty rare. There's not a lot of it. Most of the universe is empty. There's nothing there. So, an interesting observation. What we think is pretty normal for us here, look around us, I mean, there's plenty of complexity here, is actually very rare in the universe. Very rare. A very important point. Now, what is complexity? And here I put together a collection of different examples. You all can consider complexity. One for it all, a meteorite, the planet, our sun, a house with a car, or bacteria. Now, what is it that they sort of share is that the whole is more than the sum of the parts, right? That is, I think, the most fundamental aspect of it. If you, for example, would basically make a collection of little jars of chemical elements that, for example, I consist of, you put them in all these thousands of, tens of thousands different jars, that wouldn't be me, right? That would be just a collection of chemical elements. And there's no way, if you were to disassemble me and put it on all these vials, to put it together again. And there you see that it's the connections that matter. It's the variety of building blocks, the connections, and everything. It's hard to get a grip on it in terms of precise numbers, but it's clearly something that tells you the whole is more than the sum of the parts. And that is what you see in the universe, that things become more complex over the course of time. And that is strange, because you would expect to have exactly the opposite to happen. Here you have this cup with some cream on top, and someone has drawn this smiley face here, right? Someone has done that, and what is that you would expect to happen over time? You would expect it to disappear, to go away. You would never expect a cup of coffee to suddenly show a smiley face all by itself. That simply does not happen, right? You know that. So that is summarized in science as the second law of thermodynamics. Basically, everything tends to become more chaotic over time, more of a mess. That is the situation. And that raises the profound question of how is it possible that you get order and complexity? And basically, if we want to create that, we have to expend a lot of work. For example, we have to clean the kitchen. This is a drawing made by my daughter. I decided, okay, sure, I want to find a picture of cleaning the kitchen. So type it in on Google, right? And see what I can find it. I decided, no, I asked my daughter to draw a picture. And she did it. And there you see the effort you have to make to do that. And the inevitable result is that you can clean up your kitchen, but the universe as a whole becomes more messy. You wouldn't believe it perhaps, but yes, that's what's happening. Because if you have to dump the trash somewhere, you expend energy to do it. So in the end, you're creating more of a mess, even when you clean up locally. And that makes one wonder, how does the Earth exist? How is it possible that the Earth doesn't collapse in some kind of total mess, right? That's a big question. And the answer is that if you want to get complexity, what you need, and it's very basic, very simple, you need some energy flow through matter, some kind of a push that changes matter into something more complex. And you want that push not to be too hard, because then the whole thing may fall apart. It shouldn't be too soft, because nothing may happen. It needs to be just right in a way. So, and that is the case for everything. Everything that has become a little more complex has needed an energy flow to form. But then there are forms of complexity that sometimes need an energy flow to continue to exist. For, let's say, for this rock that's swinging through space, you don't really need a lot of energy. Just swinging around, nothing's happening really. But the sun, in order to shine, needs to basically combine in its interior hydrogen into helium to fuse it. That releases energy, and that is what makes the whole thing shine, and that's what causes the thing to be in a relatively stable state. And that's energy is released, is dumped into the universe, and that makes it possible for us to live on the planet, right? And every life form needs to do something more. What we need to do is take in energy, take in matter and energy continuously and dump our trash. That is what every life form is doing. The sun is not taking in energy. It uses just the available energy that's there. But life forms have to do a little more than that. They take in energy on a daily basis. If they wouldn't do that, they're gone. Right? And then we have started to create forms of complexity more than any other species. And some of these forms of complexity also need an energy flow to do what we want them to do. Right? If our car runs out of gas, it's completely useless. Right? We wouldn't want that to happen. So we need to go to the gas station regularly to make sure that this complexity does what we want it to do. Right? So inevitably this produces more of a mess. There's no way around it. That is what the second law tells us. And how do we deal with that? So if you look at the Earth then, and you think about what kind of system we find ourselves in, then you realize that we have to think of the Earth as part of a bigger scheme, namely that we're close to the sun releases that energy. For the sun it is some kind of a waste, but for us it's high quality energy. It comes down here, it heats up the Earth, it drives photosynthesis, so the plants capture that energy partially, convert it into chemical energy, that animals eat like us, and it makes it possible that we live. And then we dump a lot of low quality heat back into the universe. And that is possible because the universe is big, it's cold. So there is basically one big trash can out there that we dump our trash. And that is what drives the whole system. That is what makes it possible that on the surface of the Earth there is this incredible complexity. So as you can see, you can summarize the whole situation in very simple terms by using these very basic concepts. So what you can do is then try to trace the history of the universe in terms of how energy flows through matter have created complexity and how it all happened. I'm not going to do that now, but I want to add another example. And it's another part of the story, and it's a very important part that I just alluded to, namely that these things happen within certain limiting conditions, which I've come to call Goldilocks circumstances, following the example of what many scientists are already doing, although not in a very systematic way. I'm sure you're familiar with the story of Goldilocks and the three bears, so I may not need to explain that. But the idea is that the circumstances have to be just right, as it's called in English. I'm not completely fond of the term just right. I would say it has to be within certain boundaries. Within certain boundaries, and that depends on the type of complexity. For example, here, for us, what we would like to have is enough gravity. That is very important. If we didn't have it, we would float into the universe, we would be dead within a few minutes, right? We would also want it to be not too warm, not too cold. We probably wouldn't like to sit in the rain if it rained. I mean, here perhaps it doesn't rain that often around this time of the year, but in Amsterdam you never can tell. And there are many more other circumstances that we are important for our complexity. So you can think of us finding ourselves in a particular set of Goldilocks circumstances that make our existence possible. You can also think about the sun as requiring certain Goldilocks circumstances. What the sun requires is a big universe around it that it can dump its energy into. If that didn't exist, then the sun would very quickly heat up, explode, and wouldn't exist anymore. So the sun can only exist thanks to the fact that it's a big empty universe around it. Now, my claim is that if you combine this energy through matter approach plus the Goldilocks principle, then you can sort of come up with what you could call a historical theory of everything. And you can trace it from the very beginning, and you get a very coherent, simple story about all of history. Now, that's a grand claim, of course. And that's what when I saw it for the first time, I wasn't really sure I dared to write it down even. But I decided to do it. I wrote an article first, and then I got a chance to write my book. So that's where it is summarized. And until now, I haven't really received a lot of criticism. That doesn't mean that I've got it completely right. I don't know. But it may be a step into a direction that helps us to understand how all of history has worked. And what I'm going to do now with a few slides is to summarize that story in these terms. Let's look, for example, just at our galactic position. Not so much the whole beginning of the universe, Big Bang, cosmology. I'll leave that for others to. I mean, you can read it in my book. But let's just look at our situation in the galaxy. As I said, we are not in the middle. We're not here. We're somewhere here. This is called the galactic habitable zone. And why is that? The reason is very simple. In the center, there are lots and lots of big stars that at the end of their life explode and spread out all these chemical elements, these heavy chemical elements for the galaxy. Now, you wouldn't want to be too close to many stars that explode because they would flush out life. Simply, you wouldn't exist there. Right? So, since life has taken billions and billions of years to get to where we are now, intelligent life in the form that we know it, that is ourselves, we would not have gotten the chance to exist because we would have been flushed out by all these big exploding stars. And why aren't we here? Well, here there are too few of these stars that explode. And as a result, they don't form enough of these heavy chemical elements that we consist of, that we need for our existence, or the planet. So there is not enough stuff here to form planets and life. So here there is some kind of a compromise, enough stars that create the heavy chemical elements, but not too many that they flush out life. And that's why there is a galactic habitable zone. That's why we're here. And those are the Goldilocks circumstances for our situation, and that's what matters, right? And the same argument, or very similar argument, you can say for the sun. Well, you wouldn't want to be too far from the sun, because then the sun becomes pretty weak. It doesn't provide enough energy for life to harvest it. So you may get very simple life forms that live off geological energy, energy from within, geothermal energy, but probably not, let's say, intelligent life. You need to be fairly close to the sun, but you wouldn't want to be too close, because then, of course, you would burn. Look what happened to Venus, basically one big runaway greenhouse effect, where the temperature on the surface is more than 400 degrees Celsius. That's not a nice place to be. So you would want to be at a distance where there's enough energy that you can capture, and where there is liquid water. That's very important, liquid water. Because liquid water provides a very good environment for all kinds of chemical reactions to take place. Much better than air, and also much better than rocks and ice and solids. It's, let's say, the Goldilocks circumstances for life are in water, and it's therefore not a surprise that we consist for, I think, 65% out of water, because we emerged in water, and it's only relatively recently, only 400 million years ago, out of more than 3 billion years ago, that life moved onto the land. Most of the time life lived in water, and that is still very visible in our bodies, right? So that's why we are here and not over there, right? So that's the Goldilocks situation in the solar system. Now, the Goldilocks situation on the planet is also pretty clear. You wouldn't want to be in the core, right? It's very hot there. It consists of iron and nickel. Enormous pressure. No chance for any form of complexity like ours. The only place that is feasible is the surface of the Earth. But you wouldn't want to be too high either, even if you go up 10 kilometers or something, or I'm thinking in kilometers as a European, right? Then it's hardly possible to survive anymore. Well, we can create these Goldilocks circumstances in airplanes, for example, but then we sort of recreate circumstances that are basically at, let's say, 1.5 miles or even less altitude, because we have these pressurized cabins, right? So what you get is the surface of the Earth is a good Goldilocks environment, because on the one hand you can harvest energy from within to keep going, but even more importantly, you can harvest energy from the sun, from outside, and you can get rid of your entropy. You can get rid of your mess into the universe. So that's why we live on the surface of the planet, and that's where you would expect life to be. Right? That's where it emerged. Now, if you look, and I'm just going very quickly through the entire history, if you think about the changing surface of the Earth as a result of plate tectonics, I don't really need to explain that to you here. You're very sensitive to it, I'm sure, living in such an earthquake-prone zone. In Amsterdam, it's very different. Nothing ever happens there, right? But here you feel more like, oh, yeah, it might happen, actually, right? And that has resulted in all these changing positions of the major plates, resulting in sometimes all these continents coming together in the form of a big supercontinent like Pangaea, and then breaking apart again, and then basically drifting in all kinds of forms until we reach the current configuration, which is also just a snapshot in time. It will never be the same. It is changing while we are speaking. Not very fast, but it changes with the speed about your fingernails growing, right? That's how, for example, the Atlantic Ocean is spreading, that kind of speed. And on these shifting plates, life developed, started to diversify using these forms of energy, first geothermal, later solar energy, to diversify in all kinds of ways. I'm not going to go into that, but you have to understand it as part of a combination of geology and life that shaped each other. You cannot understand the surface of the planet without taking life into account, because life has changed it beyond recognition. By covering it, by keeping soil together, for example, where otherwise erosion would have taken everything away. Also, in other ways, microorganisms might be eating rocks, might be eroding them. Lots of things are happening that influence the geology. So there's a continuous interaction between geology and life that creates the Goldilocks circumstances for life, and it has kept our planet going for billions and billions of years. So what you find is that Goldilocks circumstances keep diversifying, especially when life moves onto land and starts covering it, which creates lots and lots of niches, Goldilocks circumstances for ever more types of plants, animals, with big ups and downs, but the trend is a more diverse population on the Earth. And what's happening also is that some species are starting to create their own Goldilocks circumstances. So birds are building nests, spiders are weaving webs, beavers are building dams, and of course, we are the Goldilocks champions on this planet. Just look around you, there's nothing natural here. Absolutely nothing, right? And even our bodies, we've really tried to change them with whatever. I mean, we put things on our faces, and I'm not going to mention everything, but we have clothes on. A lot of people use all kinds of drugs, right? So that's what we're doing. So you can summarize the history of humans as starting, let's say, a few million years ago on the East African savannas, basically trying to survive in this changing landscape. This picture is based on discoveries of ancient footsteps that are millions of years old. So this is an artist's reconstruction of what might have happened. And we find ourselves now in a situation where we are surrounded by our own complexity. I took this picture a year ago in Beijing, but I could have taken it in many big cities, I think. So this is basically human history in a nutshell, and we even have created the Goldilocks circumstances for going to the moon. I mean, that is quite an achievement for a species, I would say. So you can think of human history as us using energy, trying to create complexity in ever more different forms, even forms that are powered by energy, like engines, doing things for us that have changed the entire world. And it all boils down, in my opinion, to this simple principle of energy flows needed to create and often maintain complexity within certain boundary conditions, these Goldilocks conditions. You can summarize absolutely everything in it, I think. And if you want to challenge me after my talk, I'm happy to respond. Okay, now if this is the case, if this is indeed a structure that seems to work, what can we say about the future? And that's going to be the last part of my talk. Well, I'm not going to talk a lot about the future of the universe. If you think about the universe as a whole, it seems very likely that it will consist over hundreds, thousands, billions of years, perhaps even more than that. And it will slowly sort of peter out because it will run out of energy. But it will take some time. Right now we find ourselves in a pretty vigorous young universe where there's a lot of energy that can create a lot of complexity. So that's a situation where we find ourselves. But for humanity, maybe a little more difficult. I'm using this picture from Hawaii because on that island, people may be a little more aware of the limits of the situation. But in the end, we are all living on this planet, and we are aware of the fact that, yes, we live in a universe that doesn't really provide a lot other than solar energy and a place to dump our mess. We have to figure out how to deal with our situation on the planet itself. And what kind of future can we expect? And of course, there are lots and lots of projections, kind of techno future, kind of all-out warfare, and anything in between. I mean, it could be anything. One major point about the future is that we really don't know what's going to happen. It's not a science. I'll say a few more words about it. But the first thing I'd like to emphasize is what we want to know about the future is what we feel uncertain about. That is what we want to know. I'm sure nobody's going to pay me any money if I'm going to tell you, yes, tomorrow the sun will rise again. We all know. Perhaps people are willing to pay a little bit of money for a very good, let's say, weather forecast, although these things seem to be free now on the internet. I have to basically deal with all the ads that surround these forecasts. But yes, it's almost free. But if you think about, let's say, what's going to happen with the economy, then there are certainly people making money out of that, right? And because that is a major issue. That is what people feel uncertain about. It's very serious business. Not very different from what's happening in some local societies. I took this picture during my research in Peru. This is an indigenous healer, also predicting the future. And he makes money out of that. Not a lot of money, let's say $1 or $2 a day, but for there, it's not bad for such a thing. It's the same thing. People want to know, they feel uncertain about the future, they want some kind of reassurance, and they're willing to pay some money for that. Right? So that is what is about the future. That is what we want to know, what we are uncertain about. A very important aspect of the future is that it is a science without data. We don't have any data about the future, absolutely zero. Right? So it is not empirical science in any way. But the only thing, that goes way too quickly. The only thing we can do is construct scenarios. What more or less likely scenarios that we have to decide, okay, this may or may not happen. And how do we do that? We first start with the known trends. Like, okay, population have been growing like this. That may continue, but it may also change over time. So expected change, that's what you factor in. And then you factor in what a famous politician here in this country called the known unknowns, right? The things that you think might happen, but you're not really sure whether they will happen. Would we get a major, let's say, explosion of an infectious disease, for example? It could happen. Would we be hit by a meteorite? It could happen. So these small causes may have large effects. But at least we can think about these things. But then there's the category of unknown unknowns, things that you have no idea about, that you cannot even think of. And as an example, I would like you to go back, let's say, 500 years in time, only 500 years. Who would have predicted the Industrial Revolution? Nobody did. Nobody had any idea that it was going to happen. That was an unknown unknown at the time. Yet it happened, and it has transformed our world. So we have to think of the fact that, yes, things may happen that may completely upset our scenarios. But you cannot factor them in, because there's no way of knowing that, no way of doing that. Now, I don't know why it happens that way, but it seems to be suddenly being very active, this little remote. Anyway, now just a few examples of future prediction. This is a famous prediction by the inventor Ray Kurzweil. I'm pretty sure many people know of his book. And he argues that over the course of time, people have started to develop ever more complicated ways of externalizing, let's say, intelligence. And right now we're doing this with the aid of computers. And within 30 years, computers will become more powerful than our brains, and that will produce a major transformation. He calls it singularity. And then computers will take over. I'm not really sure whether that is going to happen, because I'm not really sure we want computers to take over, but surely lots of things are happening that seem to be beyond the control of many of us with the aid of computers. So yes, it is an important aspect of the future. Nanotechnology is another one. Making things smaller, more efficient, so less matter, less energy, trying to do same things, new things. That is certainly happening, also going to have a major impact on the future, I'm sure. But let's think about, let's say, population growth. This is happening right now. So what we see is this big takeoff in population. We're now at 7 billion, more or less, on this planet. The planet isn't getting any bigger, so that means it's a more crowded planet and will continue. Now it may sort of level off over the course of time, and that is because of the fact that more and more people live in cities, and in cities children are very expensive, so you wouldn't want to have too many of them, right? So that's why it is leveling off. And you can see this very clearly on this map, where the greatest, let's say, population growth is taking place in the least urbanized areas. And there are actually countries that are shrinking, like Russia or Italy. And also Holland would be shrinking if there were no immigration. And we're getting a lot of migrants, especially from Africa right now. But it means we have to feed them, right? We have to make sure that there's enough energy to run all these cities. How are we going to do that? So how are we going to feed the population? Can we do it organically, right? It's being promoted right now by your president and his wife. Or are we going to need genetically modified crops? It's quite a problem because the earth isn't getting bigger, right? So we have to feed more people from the same area, and we actually may be losing agricultural land because of the loss of topsoil, because we are basically building more and more suburbs or cities, and as a result losing a lot of agricultural land. All these things are happening. All important aspects of the future. So what is the consumption taking place? This is a sort of a world map of consumption, right? Get an idea of where it's happening. You see the US is, of course, a major consumer, but so is Europe, certain parts of Europe. Other parts of the world are still consuming a lot less. And that is, of course, very much tied into the energy use. Where is the energy being used? This is a world map in terms of energy, right? Also, you can see US is per capita by far the biggest energy user. That's no surprise to you, I guess. And it's the result of the fact that this country is so spread out that you need to do almost everything by car. So you cannot just go to a shop walking or on the bike, as you do in Amsterdam. No, you have to take a car. I'm not going to say that Holland is very environmentally friendly. There are lots and lots of cars in Holland, but it is less spread out in the US. And that's the case for all of Europe, I think. So that makes one wonder, what is the energy consumption? If you believe in the importance of energy flow through matter creating complexity, you want to know how much energy do we have? What are we consuming, right? So right now we're running a lot on oil, on natural gas and coal. Nuclear is there, but it's not really very big. And as you can see, the renewables, that is really very small. Makes one wonder what's happening in the world right now. If you look, for example, at the geopolitical situation in Central Asia, this is a map of where the pipelines are or planned. And there's a lot of oil and gas here, and there are not really a lot of consumers here. So what let's say the Western countries, they might call them that way, are trying to do is get it out with the aid of pipelines. But how can you do that? You would not want to run your pipeline through Iran because certain sensitivities. So basically what they're trying to do is construct these pipelines around, right? And not surprising, perhaps, that those are areas where there are lots of conflicts. I'm not going to say that all the conflicts are caused by the struggle for resources, but I do think it adds a little to it. And I think if you want to understand the world, you have to understand where the energy flows are. That's what I'm trying to say with this slide. But let's take a step back now and think about the general theme, energy needed for complexity. Here you have a statement from one of the big energy experts in the 1970s, Howard T. Odom. That was a period that energy became scarce, or so people thought, because of the oil boycott in the Middle East. And then people realized, hey, we have to think about energy. And he made this statement, all progress is due to special power subsidies. Progress was a catchword at the time. Everything was progress, right? But he said, you know what, you need energy for that. And progress evaporates whenever and wherever they are removed. So he said, you know what, we have to think about the energy. Without energy, no progress. So that makes one wonder, how much do we have? And these are tentative numbers. We don't really know exactly what we have because we don't really know how much there is, and we don't really know how much we're going to consume over the next 100 or 300 years. So these are rough estimates. But let's say we have oil for about 100 years and coal for about 100 years. Some people think there's more, but there's reason to doubt that. Natural gas, there seems to be considerably more, but quite a lot of it is down in the oceans in the form of very cold solutions called clathrates, and very hard to harvest and perhaps very dangerous because if it starts bubbling up all by itself, it's very powerful greenhouse gas, so you might cause an even more enhanced greenhouse effect. Uranium, if you were to use that on a larger scale, just a few decades, not a lot more. So we don't have a lot of energy sources that we're running our societies on. So what are we going to do? Nuclear fusion, are we going to get hydrogen or deuterium fusion? Well, it's been being researched for about 40 years. And 40 years ago they said, okay, in 40 years' time we'll get it done. Now they're saying again, in 40 years' time we'll get it done. To me that suggests that they're talking about their own, let's say, career expectancy. You expect a career of about 40 years. Okay, we can assure that, right? I'm not really sure they'll get it done. I hope they will, but I'm not so sure. So what is it that we can depend on and what can we do? So I think the only source that we have, and that's not totally surprising, is the sun. So you want to know where is the sun shining, what is going to happen. So you can calculate how much energy you can get from a certain area. So let's say 300,000 square kilometers here in the Sahara, enough to meet the world's demand. And you could put your solar in New Mexico, Arizona, and you could also achieve a lot. Now, of course, that would create some problems. Here in the US, you're very fortunate to have it within your own borders, but here in the Sahara, it would belong to someone else, and one might wonder, what kind of social problems is that going to create, right? Are you going to have a new elite there that's going to earn a lot of money for eternity, forever? What are you going to do with that money, right? Are we going to allow that to happen? Would we get another wave of colonization, for example? That might happen. It might lead to new wars, but then over deserts instead of over oil. But also you can think about the price. Right now it is not cheap enough to put solar on your roof. I mean, it's cheaper still to burn coal or gas. But the price is coming down. So here you see the price of, let's say, the price of solar cells. And it's expected that somehow, if indeed the prices for fossil fuels are going up as expected, and these prices are coming down, they will cross. And if that's the case, then solar will become profitable and people will start doing it on a large scale. Now, I'm not really sure this graph is correct, but the general principle is there. That's going to happen at a certain point in time. And there are signs that this is happening. More and more solar being put on roofs. Germany is an important leader, and the Vatican has put solar on its roof, as you can see. Not surprising, perhaps, with a German Pope. So that's all happening, right? The next form of energy is wind energy. You want to know where the wind blows, and you can sort of make these maps, and the Dutch are very good at that, of course, because we have long experience with windmills. But also this is happening. Did you know that? That you have these new sailing ships that use big wind sails to help reduce their fuel costs? I think very interesting development. Also, you have these bigger windmills to get an idea of what's been happening. These were the windmills size in 1980. This is the size right now. This is the big Ferris wheel called the London Eye in London. So bigger than the London Eye. That's the kind of wind turbines that are being constructed now. You probably can't make them any bigger than this, because then the tips of the wings will go supersonic if they start, and that's not what you want to happen. That's real too complicated. But this is happening. You get all these wind parks in the North Sea, for example. Of course, you had them already in California quite some time ago. But what they have in common is it's less concentrated energy. It's more extensive than the kind of fuels that we are using. So it will become more difficult to create complexity as a result. So basically, if you look at it from a distance, what is it that we can expect when we will go through this transition from a fossil fuel economy to, let's say, a solar economy? Is basically that you would want to have possibilities for generating electricity wherever it yields the most and wherever you can do it. So you're probably going to think about integrating it into your buildings. That's happening right now. But you would do it very systematically. You would get building codes that probably mandate solar energy wherever it can be done. Of course, you want to increase the efficiency of it. That's no news. But the important thing is that we have to start thinking about a very integrated way of thinking about energy. But there may not be enough to maintain our current lifestyle. I think that is certainly a possibility. And as a result, our complexity may go down, the complexity that we are making. We have to keep that in mind, that may be happening. But what is it that we will need it for? And this is now going to summarize the whole story. Basically, we'll need it to maintain our complexity. That's what we'll need it for. We'll need also to combat the mess, the entropy that we create by doing all these things. We have to create all kind of artificial recycling. Until now, we have mostly relied on natural cycles that have developed on the Earth during its long history, but we're creating way too much stuff. We cannot rely on that anymore. We create our own recycling. But since that is a new form of complexity that requires energy, you'll create more entropy as a result. So this seems like a vicious cycle, right? You're trying to clean up, but you're making more of a mess. How do you get out of that? So how do you do that? And the answer is you have to think about what kind of entropy you're creating, what kind of a mess. If you create, let's say, material entropy, that you spread out everything over the Earth and you cannot really get it back, concentrated forms without spending a lot of energy, that's bad. But if you can try to shift the balance as much as you can to create radiation, this low-level radiation that you can just get rid of in the universe, that's good. Well, that's the way to get rid of it. So we have to think about this balance of material entropy and radiation entropy. How can we do that? And I think that should be a leading theme for our considerations for the future. Think about these things, whatever you're doing. Anyway, I'm now approaching the end of my talk, but then you get some big questions. Can we actually do that? Are we genetically hardwired, one may wonder, to actually harvest a little more than we actually need? The reason for that would be that it's a good idea to do that because the supply of energy fluctuates on the Earth. We have summers and winters, right? So it may be a good idea to store a little here and there, to harvest a little more so we have some left when there is less of it. So perhaps we are, and also in terms of survival and competition, we may be genetically sort of programmed to harvest more than we need. I'm not saying it is the case, but it's certainly interesting to think of it, and we may try to investigate that. If that's the case, then we may wonder, can we tame this biological instinct, if it exists, with the aid of our learning, our culture, our software in our brains, I would say? Is that possible? I think these are the big questions we have to think about. Could we do that, and what is required to do that? Well, now, returning to this picture, I hope that you understand that by contemplating life on the Earth in a more detached way, you come up with all kinds of intellectual schemes that may be helpful to understand better what has been going on all through history, and perhaps may help us to understand what needs to be done to secure a reasonably safe future for our kids, our grandkids, and whoever will come after them. Well, I hope that you will have, let's say, that I be able to get across what I wanted to say, and I hope you'll have enjoyed at least this presentation. Thank you very much. Thank you.